We are ready now to turn our attention to the second main topic in this section, which is planes. So let's take a look at planes. In R3 again, we're going to need two things to find an equation of a plane. And one of those things is, of course, going to be the point on the plane. Any point will do. Doesn't have to be a particular point. Any point will do. That shouldn't be too hard. There's infinitely many of them. And the second thing we're going to need is what we call a normal vector. And that is to say a vector which is orthogonal to the plane. Again, any vector which is orthogonal or perpendicular to the plane will do. Let's draw a picture. Suppose I've got some plane living here in R3, and let's suppose I know those two things. Let's suppose I know some point right here that is on my plane. I'll call it x naught, y naught, z naught. And let's suppose I know some vector. Let's call it n for normal vector, because it makes a right angle with the plane, orthogonal to the plane. All right, so let's pick any other point that I want to be on my plane. Right here, let's call it x, y, and z. So I'm going to form a vector then that goes from my point that I know is on my plane to the point x, y, z that I want to be on my plane. Now, what's going to be true about this vector and its relationship to n? It's going to have to be orthogonal to n. Let's go ahead and give n components of a, b, and c. So this vector here of, let's see, the one starting at the point I know is on my plane to the point that I want to be on my plane, x minus x naught, y minus y naught, z minus z naught, if it's on the plane there, is going to be orthogonal to n, our normal vector, which again we've given the generic components of a, b, and c. Well, what does that mean? Well, one thing it means is that the dot product is 0. So all I do is take this vector, x minus x naught, y minus y naught, z minus z naught, dot it with my normal vector, and I know I have to get 0, take that dot product, and my equation comes out. I've got a times the quantity x minus x naught plus b times the quantity y minus y naught plus c times the quantity z minus z naught equals 0. And there is my plane equation. Of course, you can put it in different forms, and we'll see that as we look at examples. But there's the basic idea. Let's take a look at an example now. Let's suppose I want to find the equation of the plane that goes through a particular point. That's one thing we need. Point is 2, negative 1, 4. And let's suppose it has a normal vector. So we're just given the normal vector here. Again, we'll call it n, and we'll say it has components negative 2, 1, 5. All right. So very simple. Again, here's our plane. We've got some point on here, 2, negative 1, 4. We've got some normal vector n that has the components negative 2, 1, 5. And we simply pick another point, x, y, z. We form the vector from 2, negative 1, 4, 2, that generic point we want to be on our plane x, y, z. That has to be orthogonal to that normal vector. And so we have that x minus 2, y minus minus 1 or y plus 1, z minus 4, there's the vector on my plane, dotted with negative 2, 1, 5 has to be equal to 0. So I've got negative 2 times the quantity x minus 2 plus 1 times the quantity y plus 1 plus 5 times the quantity z minus 4 is equal to 0. Now I'm going to go ahead and put this in standard form. I've got negative 2x plus 4 plus y plus 1 plus 5z minus 20 is equal to 0. So I've got negative 2x plus y plus 5z. I'll throw all my constants on the right. What's that going to be? I think a positive 15. Check my math there. That's a standard form for an equation of this particular plane. Let's try another example. Suppose we want to find the equation of the plane that contains a particular line. Given by the parametric equations, x equals 2 minus 5t, y equals 3 plus 4t, and z equals 8 minus t, and is parallel to the plane given by the equation 2x plus 3y minus 6z is equal to 10. Alright, so here's our situation now. Here's the plane that we're trying to find, and we have some line that runs through this plane. Let me just draw some line running through this plane here with those parametric equations. X is 2 minus 5t, y is 3 plus 4t, z is 8 minus t. I've got another plane existing in space which is parallel to the plane I'm trying to find. I know something about this plane. In particular, I know its equation. 2x plus 3y minus 6z equals 10. Look back at this last example. Our standard form was negative 2x plus y plus 5z equals 15. Negative 2, positive 1, positive 5. Negative 2, positive 1, positive 5. That will always be the case. In standard form, the coefficients on x, y, and z can be used as the components of a normal vector to that plane. So if I come back down here, I've got a normal vector to this plane, I'll call it n, which is equal to 2, 3, negative 6, the coefficients of the variables on the standard equation of that plane. I can move this vector anywhere I want. Since these two planes are parallel, well, this vector n is also going to be orthogonal to the plane that I'm trying to find. So I've got my normal vector. That's one thing I need. Another is a point on my plane. Well, remember how we can find a point given a line. Any point on this line will do, so we can just let t, our parameter, be anything we want. I'm just going to go ahead and make my life easy. Let t be 0. Then x is 2, y is 3, z is 8, putting t equals 0 in for those parametric equations. So I've got some point here then, let's say right here, of 2, 3, and 8. And now I just pick any other point, x, y, z, form this vector. And so I have x minus 2, y minus 3, z minus 8. Sorry, I'm laughing. My daughter's trying to break into my office. That's equal to, what is that equal? Oh, no, that's not equal to anything. That has to be orthogonal to my normal vector of 2, 3, negative 6. So their dot product must be 0. So I've got 2x minus 4 plus 3y minus 9 minus 6z plus 48 is 0. Putting this in standard form, 2x plus 3y minus 6z is equal to, I don't know, what's that equal to? Whatever. 48 minus 9 is, 39. Minus 4 more is 35, so it'll be a negative 35 when I bring it over here. Check my math there, but I think that's right. Okay, let's do one more example of finding the equation of a plane. So let's suppose I want to find an equation of the plane that goes through 3 points. Remember, we've talked about this before. 3 points in R3 determine a unique plane. Let's suppose our points are P at 1, 2, negative 5, Q, which is at 3, negative 2, 1, and R, which is at 0, 4, negative 2. That's 0, 4, negative 2. Okay, again, we need two things, so here's what I'm going to do. Here's how I'm going to approach this. I've got my plane here, and it has my 3 points on it. Here's, say, P, here's Q, and here's R. Clearly, I have a point on my plane. That's one of the two things I need. I have actually 3 to choose from. How am I going to get a normal vector? A vector orthogonal to this plane. Well, I'm going to form the vector from P to Q. I'm going to form the vector from P to R. And then I'm going to cross PR with PQ. Remember what that's going to give me. PR cross PQ using the right-hand rule Pull my fingers down the vector PR, curl them towards the vector PQ. My thumb of my right hand points in the direction. This is PR cross PQ. That will be a normal vector. Remember, it's orthogonal to both of the original vectors in the cross product, so it's orthogonal to that plane. And that'll be my normal vector. So the first thing we want to do then is form PQ. So from P to Q, components of Q minus components of P, that's 3 minus 1 or 2. Negative 2 minus 2 is negative 4. 1 minus a minus 5 is 1 plus 5 or 6. How about PR? PR, let's see, from P to R, 0 minus 1 is a negative 1. 4 minus 2 is 2. Negative 2 minus a minus 5 is negative 2 plus 5, which is a positive 3. So let's take now PQ. Actually, let's take PR cross PQ just to make it look nicer on our picture. We could do the other way as well. We just send our normal vector going down. That's fine. But I'm going to take PR cross PQ, so IJK. Let's see, negative 1, 2, 3, 2, negative 4, 6. And we get I times, let's see, 12 minus 12 is 12 plus 12 or 24. Minus J times negative 6 minus 6 is negative 12. And let's see, plus K, which is going to be 4 minus 4 or 0. So I have the vector 24, 12, 0. Well, I'm going to use, for my normal vector, a scalar multiple of that. Let's just use 2, 1, 0. Just divide everything by 12. So we found this big long one. What I'm going to use for n actually is that thing, a 12th of that. Here's my vector n, which is 2, 1, 0. Okay, so now we're in business. I'll use, I guess I'll just use P as my point. What's this point here? 1, 2, negative 5. So form another vector from P to x, y, z. So I've got x minus 1, y minus 2, z minus a minus 5 or z plus 5. Dotted with 2, 1, 0. That has to be equal to 0. And so I've got 2x minus 2 plus y minus 2 plus nothing is 0. And so here's my standard form, 2x plus y. This should be a 2 here, not a z. Yeah. Is equal to, looks like 4. There's the equation of my plane. And so that leaves us with one thing and one thing only, and that is your password for 9.5 to get into your homework, which I know you're dying to do. Lines and planes, a lot of good stuff in there. Apotheosis is your password, APOTHEOSIS. And that just means elevation to divine status. It can also mean the perfect example. You may have thought that one of my examples there in that lecture was just the apotheosis of an example for lines or planes. I don't know, and maybe you've elevated this section to divine status, an apotheosis of this section. Either way, I'm sure you're going to have a good time doing it, and if you get stuck at all, please let me know. I can answer any questions that you may have.